Hey everyone, so we are giving a talk today about the things that we had to do to get Druid to play nicely with SQL and Superset. First, some quick introductions.
Hi, I am Jingshan Rupert Wu. I work as a software engineer, and I work on several big data tools, including Superset and Calcite, and also Druid.
I'm Ganesh Kota. I've worked at Oath for like 4 years now in the big data space, so yeah, and we work on the same team. So let's talk about Druid use at Oath. Druid is pretty heavily used at Oath in many different production systems for a couple different reasons. It is really scalable. There are Druid systems at Yahoo which ingest up to like 1 million events a second. And it's really good for serving real-time data with really low latency. And it's also really good at storing aggregate data. So because it's good for these sort of use cases, we find that a lot of people in Oath want to sometimes do ad hoc queries on event data through Druid. So this is great, but there are a couple different problems with this. The main problem is the JSON input format that Druid uses. If you want to query Druid, then you have to go use the JSON input format, which is a little bit difficult because it's hard to interact with, and a lot of people, especially non-technical users, are not familiar with how to optimize JSON queries or construct JSON queries. So we decided to use SQL to bridge the gap. So what we wanted to do is we wanted to find a way to query Druid with SQL relatively effectively and efficiently. SQL is great because it's essentially the lingua franca of data. Everyone who is familiar with data already is familiar with SQL. And people at Oath, even many non-technical users, are familiar with how to write a good SQL query. And the other great thing about SQL is all BI tools and all those other tools also support SQL very, very well. So this is a quick example. Here's a sample SQL query. And it's like a pretty standard query. It has a select, it has some aggregates, has some filters. And so this is like a pretty typical SQL query that you might write. But the equivalent JSON query for Druid is quite a bit longer. You can see you have to have, you got to select the type of query that you're going to run, then you got to select your filters, then you got to select your aggregations, your filtered aggregations, and then the interval that you want to run the query for. And a lot of people are just like not familiar with how to do this. So we looked into a couple of different solutions on how to bridge SQL with Druid. And these are a couple of different solutions that we looked into. The first one is Druid SQL services. So Druid actually does natively support SQL. The problem we found with this is that support is a little bit experimental, and not all SQL features are supported. And the other problem for us in particular is we didn't want to tie the version of Druid to the version of our SQL parser, right? Because if we get faster updates to the SQL parser, we might not update Druid as often as we want to update our SQL parser. The other thing we looked into is the Hive Druid connection. The Hive team has done a lot of work in Druid in the last couple of releases, and now it's pretty good. But at the time, it didn't support a lot of the features we were looking for. And we dug a little deeper, and we found that under the hood, Hive Druid actually also uses Apache Calcite, which is like a powerful SQL parser and planner. And we decided that since Calcite is open source anyway, we just use Calcite directly. And then if there were any deficiencies, we could just contribute ourselves and fix any issues that arose. So now Rupert's going to tell you a little bit more about Calcite and the changes that we had to make to get this all to work.
Hey, so like we mentioned before, Calcite is open source. That's pretty much the first reason we are going to pick Calcite. And Calcite is basically a translator between SQL and Druid JSON query in our use case. But it is actually an industrial standard SQL parser that works on different kinds of non-SQL database, such as Cassandra and MongoDB. The core idea of Calcite is to get the relational algebras of the SQL query first, and then transfer the relational algebra trees using different planning rules. And then we will also use the optimizer to pick the final results to run. It also has a cost model to compute the cost of each relational algebra tree. So then it will pick the most efficient route to run the query. I will go over this whole process in the next few slides. Right now it is internally used by another Druid SQL service we mentioned before too. Pretty much the core algorithm of another SQL services like Hive Druid connections and Druid native support of SQL. So the last one is open source, yes. So first, let me go over the core ideas, calcite relational algebra. So basically, it would translate SQL statement into a tree structures with nodes representing the logics in it. So for examples in here, on the left side is a query SQL statement, and the right side is the relational algebra tree that representing the same logics as the SQL. I will go over nodes one by one. So the first one, table scan nodes, actually lock down which tables you are going to query. And the second one, filter nodes, is equivalent to the where clause in SQL statement. In here, we only query the rows with columns b equals to 1. The project node is not so obvious, but in many databases, the actual column names may contain namespace or use the index as the column name. So the project nodes will take care of this kind of translation between the column names you notify in the SQL query and the actual column name in the database. The next one is the aggregate nodes. It usually contains most of the computations in the SQL query. In here, we are the aggregate node represents the summation functions we use on column 8. The last one is sort nodes, which corresponding to the order by clause in SQL statement. After we have the relational algebra tree, then it is the planning phase. With the relational logic trees, we now can transform the tree to another one representing with equivalent logics. So we developed several rules on that. So the logic tree will collide with rules. If the rules is applicable, a new logic trees with equivalent logics will be generated. Different use case will have different set of rules for different purpose. In these examples, there are two Druid-related rules that can transform our initial logic tree. The first one combines 4 nodes from table scan to aggregate, and combine them as a Druid group by nodes, which has the equivalent logics, and the sort node is left as it is. The second rule combines all 5 nodes together as a Druid top-end node. All 3 logic trees here represent the same logics, but they may have different costs. Also, in the end, we need the logic trees with Druid nodes inside, so we can translate the Druid nodes into a JSON Druid query that we can request the data from Druid. So now we have 2 results trees. Which one to pick will be the questions to ask for optimizer. So now we have 2 trees with equivalent logics. To pick the one with more efficient, one, calcite will optimize based on the cost models. Each node in the calcite will have its cost to quantify the computational power required to run the logics in the tree. The final results to be used will be the trees with minimum cost. Back to our examples. The cost of the final trees on the top is 10 plus 10 equals to 20. But another output trees will only have 1 with 15 costs. The optimizer will then pick the Druid top-end node, which is the bottom one, as the final results. But actually, in real calcite use case, the cost sometimes depends on the numbers of the rows that the nodes will take. And different types of the node may also have different costs. In the Druid use case, the basic idea of the optimization is to push more computations in Druid size and reduce the computation required in calcite local machine. So after we have a choice of the tree, the next one is to actually fetch the data from Druid. Oops. That's the job of renderer. So renderer is basically a JSON writer that would generate a JSON query to request data from Druid. And we also parse the return data from Druid into a format that Calcite understands. If there are more computations to be executed before we can return the final results, the Calcite will run another necessary computations. At the time when we try to use Calcite, it still have several deficiencies before we can really apply it into our Druid cluster. So we decided to make contribution back to the community. The change we make mostly inside the Druid adapters, which we add or change some of the rules and also add new renderers for them. Let me go over the deficiencies before our change. These are three major ones that we work on. First one, it is a support on condensing aggregates. Calcite prefer to provide user with exact condensing results. It is maybe the standard in SQL, but in our use case, there are too much rows in Druid datasets. We need estimation method, like data sketch or hyperlog to quickly estimate the cardinality in the data. Druid has the support of cardinality estimations, but we need Calcite to be able to use it. Back into the version that we developed, it's still not supported yet. It was still not supported yet. I will also explain a little bit about data sketches in the next slides, but let me keep going. It's about another deficiencies. So the second one is Calcite in the time did not support on post-aggregate. Part of the computations in functions like average will be performed in Calcite instead of Druid. Moving those computations to Druid can save memory and times when we're actually running the query. The last one is the support of filter aggregate. Without the support, Calcite may assign Druid to query all rows to do the filters and aggregate them in Calcite local machine. This could cause a huge fallbacks in performance when filtered aggregate is involved. So let me talk about the data sketch support first, which is get merged in as Calcite ticket 7087. So the concepts of data sketch, like I mentioned before, is used to estimate the cardinality in data. It is extensively used in streaming data cases. It fits our use case very well because it trades off the accuracy for speed. Users can also configure thresholds on it. If the cardinality in the data is less than that, sketches can produce exact results. After that, sketches will give approximate result. The error bound of the approximate result is also mathematically provable. So user can have a control of the results of the estimation. It also allows the set operation like union, intersects, and difference on your data sketches columns. They're very useful in streaming use case because when new data is coming, we can run the set operation between old data and new data to generate the new results. Then we don't have to run the algorithm all over again. So to enable the data sketches support in Calcite Druid, we add new rules to translate distinct con aggregates to data sketches JSON node. So Calcite can render the Druid JSONs that being able to use the data sketches method. But some users may still need to use exact cardinality distinct cont. To do that, they can configure whether the approximate cardinality is allowed, or configure the exact thresholds of data sketch I mentioned before. So let's look at the performance. The improvement in the performance is also great. It reduced the running times greatly when the query is doing condensing. And also, if you allow the approximate cardinality. In the test query we run in our data, the running time is reduced from 9 seconds to 1.3 seconds. Also, after we have this functionality enabled, there are a lot of existing data sketches columns in OAuth data. With this support, our users can utilize those columns through Calcite. The second support we did is the post-aggregator support. It get merged in as in Calcite ticket 1803. We also add new rules to merge post-aggregation zone in order to support Druid query node. The final tree can include post-aggregation logics. Also, new renderers is built to query with the post-aggregator. Now, when possible, the post-aggregations will be pushed into Druid query node and computed in Druid cluster. This support also allows more use case with the data sketches set operations, because most of the set operations is done by post-aggregation in Druid. The last one is the filter aggregation support. We also build new rules for it. I may need a graph to explain about the new rules. Before our change, when there are filter aggregated in SQL, Calcite will fetch all rows from Druid without any filtering and pruning. Then Calcite will execute the filter and aggregate the logics locally with all the rows we fetch from Druid. But after our change, the new rules will figure out the common filters from all filters on the aggregates and combine it with the outer filter. Since Druid can understand the outer filter, so Druid cluster will prune the data for Calcite with common filters and returns only necessary rows to Calcite. Calcite then actually process a lot less row than before. Filter aggregates will still be executed in Calcite though, but with a better pruned data. So we can see the improvement in performance. It is also great when the filter aggregator in mode. It reduced the running time from 43 seconds to 1 second in our test query. Basically because like Druid right now returns pruned data, and Calcite doesn't have to produce or process all rows on the return data. So next one, I will go ahead and talk about the user interface. We use Superset with Druid extensively in Oath. Superset is a data visualization tools that work with different kinds of database, including non-SQL and SQL1. For SQL database, it has features called SQL Lab to allow users to write ad-hoc SQL query and run it on there. Since we have Calcite supporting Druid now, we can try to connect SQL Lab with Druid. Before we can do that, we need a connector between Superset and Calcite. Since Calcite is a Python application, we implement a standard Python DP API to wrap the Calcite connection logics. Right now, it is internally used with Superset in Oath. So this is the whole architectures of Druid queries SQL services we have. User will first write a SQL statement in SQL Lab. Then Calcite JDBCs will send out a SQL to Calcite. Calcite will parse, plan, and optimize the SQL statement. The results will then be used by SQL adapter to fetch data from Druid. Druid cluster will run most of the computations. If there are computations that's still necessary, before we can return the results, Calcite would run it locally. The final results will be sent back to the Superset, and users can view the results from the UI of Superset. So let's do a demos on our interface.
All right, so we're going to show like a simple demo of what's now possible now that we've done all this stuff. So 1 second. So this is our Superset instance, and we've set it up to work with SQL Lab, and you can see it's connecting to Druid in the backend. If we look here, like you can see that this is our Instamart DataWorks example, datasource and Druid, and then you can see that's the same data source that we're about to query right now. So first, just to give you a size of the data that we're looking at here, I just want to run sum of record count. So right now there's like 7.4 billion rows in this data source. And next, I want to show you this query. So this is a count distinct query. This, is that what you're saying? Yeah. All right. So this is a count distinct query. This goes back to the data sketch support that we added earlier. Because in Oath, basically, or at least in the way we use Druid, pretty much all count distinct queries are stored as data sketches. And you can see here browser version is stored as a binary. So this query would not have been possible through Calcite before our changes. But now you can see it works. And that's pretty slow, but hang on. Yeah, I'm not sure why that's so slow. That was much faster yesterday. Anyway, you can see there's 169 distinct browser versions in this data set. The other thing that we added is filtered aggregates. So this goes back to this slide right here. So you can see here, originally, Druid would fetch all the rows, and then the filtering would happen exclusively on the Calcite side. But then now we can extract common filters and do that ahead of time. So you can see here, the common filter is browser name equals Apple Safari and browser name equals Google Chrome. So those two filters can now be performed in Druid instead of in Calcite. And so that we found greatly improves the performance. So if you run this query, then you can see there's 28 different versions of Apple Safari in this data set, and there's 69 different versions of Google Chrome in this data set. So these are just some examples of what we can now do. And yeah, and then the other thing is, as we said earlier, in order to connect Calcite to Druid in the first place, we had to write this Superset Calcite Connector. And once we did that, then it all pretty much just worked. So yeah, that's basically it. And do you have any questions, comments, anything? Yeah. The connector, we tried to open source. What happened? What's the story with that?
We are not open sourcing it right now. It's probably some. So not sure whether we can work with all versions of Superset. So we make sure some compatibilities on that. So we can open source it, but since not coming up with so many use cases for now, so we probably will do it later.
Yeah, so that's in progress, basically. Yeah, go ahead. One other question.
Yeah, is there an easy way to see the query plan at all, or do you need to enable logging of the queries on the Druid side to kind of see what we're coming up with?
You can do that if you use the Calcite CLI, but through Superset, it's a little difficult, basically. Yeah.
Could you elaborate on some of the challenges you had with queries that led you to using Calcite over Red?
Yeah, so some of these features, so Hive underneath the hood uses Calcite. So basically, like, since these features weren't supported in Calcite before, they would not have been supported in Hive before. Yeah. Anyone else? All right, I think we're basically done here. Cool.